1, 2. Welcome to today's live stream. We're going to do sheet 14 again from Monday, which actually wasn't a very good stream. So we're repeating that sheet. We're starting off with question 1, which is quite a straightforward proof. You want to show that tan 2a equals this. And it should only take you a minute really to have a go at this, because you'll either be able to do it quickly or you won't. Okay, so there's two ways to do this. You can either use tan a plus a and use the fact that that's going to equal tan a plus a over 1 minus tan a, or I'm just going to show you using sine 2a over cos 2a, because that's what tan 2a equals. And so therefore I'm going to get 2 sine a over times by cos a for the top. And the bottom, what I'm going to use is cos squared of a minus sine squared of a is equal to cos 2a. Now if I divide the top by cos squared of a, I'm going to get 2 sine a cos a. One of the cos is going to cancel. Let's just write that out so you can see it happening actually. So we're going to divide the top by cos squared a. So that's the top divided by cos squared a. And then I'm going to divide the bottom also by cos squared a. And what we can see here is cos a will cancel out with that to leave us 2 tan a. And we've got cos squared divided by cos squared is 1, and sine squared divided by cos squared is tan squared. So I get 1 minus tan squared a. So that is better written as 2 tan a over 1 minus tan squared of a. Right, next question. Question 2. I'm going to show there's no stationary points to this, so that's a bit more of a thinking question. I'm going to give you about 3 minutes to have a go at this one. Right, so first of all, we need to find dy by dx. So let's do that. So dy by dx, and this is the product rule. So differentiate the x, we'll get cot x is 1 times by cot 2x. Differentiate the cot x, then we're going to get minus 2 cosec squared 2x. And then we're going to times that by x. So we get minus 2x cosec squared 2x, because cot goes to minus cosec squared. So we've got that. Now we want to show that it has no stationary points. So if we make dy by dx equal to 0 and try and solve this, we can see this is equal to cos 2x over sine 2x minus 2x over sine squared 2x, because cosec 1 over sine, so cosec squared is 1 over sine squared, so we get 2x over sine squared 2x. So we've got times top and bottom of this by sine 2x, so we get cos 2x sine 2x minus 2x all over sine squared 2x. Now, if this is to have stationary points, then the top of this fraction must equal 0. So that implies 0 is equal to, now cos 2x sine 2x, that's the same as sine 4x, but sine 4x would go to 2 lots of that, so we need to make this a half, minus 2x. So, for this to equal 0, okay, we need to find, let's transfer out by 2, and, well, let's take the 2x to the other side, so we get 2x equals a half sine of 4x, times by 2, we get 4x must equal sine of 4x. Now, a quick sketch of what's going on will help us. So here's y equals 4x. And here is, I'm going to draw y equals sine 4x. Now, what we can see is they cross at x equals 0, but cot is not defined for when x equals 0, because you've got cos over sine. And if you've got cos of 2x divided by sine of 2x, sine of 2x is, sine of 0 is going to be 0, so this is undefined. So the cot is undefined here. So, so there's no solution. So no turning point. At x equals 0. Also, what we also know is that the gradient at x equals 0 of y equals 4x is equal to 4. And sine of 4x, the gradient of that, also at that point is 4. So they both have the same gradient at this point. But from there on, sine x decreases that way and it gets less steep this way. So therefore, it's never going to cross again. If the gradients were different, say sine x started off being steeper than this curve, then we'd have more crossing points. But as that is not the case, we don't have any more crossing points. So therefore, we have no stationary points. So we have no stationary points as they do not cross again. And you've probably got to say something about the relative gradients, which I just mentioned then. Right, the next question. And what I'm going to do is change this 8 to a 4, because with 8, that doesn't actually come out to an answer. So that we're going to make this equal to a 4 so that we can actually get some real solutions to this problem. I'll give you, it should take about 3 minutes to do that. Okay, so let's get straight to this one. So we're going to rewrite the cos squared as 1 minus sine squared. So we get 6 1 minus sine squared x minus sine x equals 4. So we have 6 minus 6 sine squared x minus sine x equals 4. What I'm going to do is I'm going to change all the signs on this side and then take the 4 across. And I think I may have made a mistake here in trying to fix this answer. So what do we get? We get... No, I don't. Let's just note. What I'm going to do is, sorry, I'm just trying to do 2 steps at once. Let's just bring the 4 to this side. So I'm going to get 2 minus 6 sine squared x minus sine x equals 0. Change the sign of everything to get 6 sine squared, just because I find it easier to factorise like that. So, and I'm sure many of you will do too. Now I can factorise this. So I get 3 sine x, and I get a 2 sine x equals 0. And what I'm going to do is I want a plus sign, so I'm going to make this equal to, I need a minus somewhere, so I need a minus 1 there, and I need a plus 2 there. So that gives me 4 sine x minus 3 sine x, give me sine x. So therefore sine x will equal minus 2/3 or a half. And then if we get the minus 2/3, I think a calculator will give us something negative over here, about minus 41. So we need to find the two values here and here. And this one is obviously that distance the same as this distance, so add it on to 180. And we get 221 there, 0.8. And then at this one here, okay, that's going to be 360. Take it away from 360, we get 318.2. And half, so there's our half, that's at 30 degrees, should know that off by heart. And the next one's going to be 180 minus 30, which is 150 degrees. Right, next question, here we go. Question 4, there's a little bit more to it. I'm going to give you 5 minutes to have a go at this question. 1 minute to go. Right, here we go. So we've got somebody blowing perfectly spherical bubblegum, was quite impressive, and inflating it at a rate of 5 centimeters cubed per second. Write down an expression for its volume in terms of its radius. So, volume in terms of its radius, the volume is going to equal 4/3 pi r cubed if it's a perfect sphere. Hence, find the rate at which its radius is increasing when it has a radius of 8. Well, we know that the volume is increasing, dv by dt is equal to 5 centimeters cubed per second. But we want to find the rate at which its radius is increasing, well, dr by dt. So we need a relationship between dv and dr, so we can turn this into dr by dt. So we differentiate this. So we get dv by dr will be equal to 3 times that is 4 pi r squared. So dr by dt will equal dv by dt divided by dv by dr. No, it won't. Sorry. Yeah, it is. Sorry. Yeah, dv by dt divided by dr by dv. Or we could write it as, it's not divided by dr by dv, divided by dv by dr. But if we do dr by dv times dv by dt, you can sort of imagine the dv's cancelling. So dr by dv is going to be 1 over 4 pi r squared. And we're going to times that by 5. And we know r equals 8, so we've got 64 times 4, which is 256. That's going to be equal to 5 over 256 pi centimeters per second. Now for part C, find an expression for its volume at a time t seconds after she started to inflate it. So we know that we've got dv by dt and we want to find an expression for volume. So if we integrate that with respect to t, that's going to be equal to the integral of 5 dt. So that's the integral of dv, so that's just going to be v. That's going to be the integral of 5 dt, which is 5t plus c. And we know that the volume will be 0 at time t is 0, so therefore c will equal 0. So v will equal 5t. So when the radius reaches 10 centimeters, the bubble bursts, the potential results and all that. How many seconds of blissful inflation have passed before the bubble pops? So we know that's 10 seconds, so therefore, sorry, what am I doing? I'm just looking at my previous answer, and I think my previous answer's incorrect. So just give me a second to think, just check. 4/3 pi r cubed, yes it is. So we know that okay, yeah, we need to find the volume. Sorry, I'm being a bit dozy. So we need to find the volume. So the volume is equal to 4/3 pi r cubed, which is equal to, let's just give myself a bit more space to work with. I'm going to move into the next question. So it's going to equal to 4/3 times pi times 1,000. So that gives me 4,000 pi over 3. So that's my volume, and I know my t, v is equal to 5t, so t will equal 1/5 of that. So t will equal 800 pi over 3 seconds. And if you want to actually work that out in seconds, it's about 838 seconds. Sorry about that, just had a bit of a mind blank there. Right, next question. Is question 5, and what I've done here, this is dependent on 2 previous questions that we've done, and I've highlighted the most important bits in yellow for part A and in green bits for part B, and leave you to try and work out what C will be. And bearing in mind I'm directing you towards the answer, you should be able to do this in 2 minutes. Right, so what we've got here, we've got f of naught equals 1, g of naught equals a of naught. So if we're trying to make f and g equal, so the y-intercepts are the same, so that means f of naught and g of naught are the same. So if f of naught equals g of naught, so we've got f of naught equals g of naught, which is equal to 1, which equals a naught. So a naught will equal 1. For part B, we've got f dashed of x sine minus equals minus sine x, and when we put naught into that, we get f dashed of naught equals naught. So g dash of naught equals a1. So therefore a1 will equal 0 in this case. And so what we're trying to do is, for a2, we're going to try and find out what the second derivative gives us. So f double dash of x in this case, this was the cos function doing here, is minus cos x. Find f double dash of naught, we get equal to minus 1. And g double dashed of naught was equal to 2a2. So therefore, a2 must equal minus a half, okay, because minus 1 must equal to a2. And this is, for those who've gone through and done Maclaurens already, this is just the first 2 stages of Maclaurens, and we'll get to a more formulaic way of doing Maclaurens ready for doing proper exam questions on it in due course. Right, next question. Question 6. Find the series expansion of this. I don't think this should take more than, let me just have a think. It shouldn't take more than 3 minutes to do. So let's give you 3 minutes to have a go at this one. Right, so what we need to do is we need to take the first brackets here. And we don't need to expand that. We just need to multiply that by the x and the x squared terms are needed from this bit here. So from the x squared, x plus 4 to the 5, we only need the x and the x squared terms. And the x term is given by 5, choose 1 of x times by 4 to the power of 4. And then the x squared term is given by 5, choose 2 of x squared times 4 cubed. So we're just going to times this out by this, and we only need the x squared term when we do that as well. So we've got 2x plus 3 times by, this comes out as 1280x plus 640x squared. So we just need to times that by the 3 and that by the 2x. So we get 2x times 1280x plus 3 times 640x squared, which gives us 4,480x squared. So the coefficient is equal to 4,480. Alright, now we'll finish off with quite a nasty little proof for you to try and see if you can get out. So here we go. And sorry, I haven't changed the question. So here we go. There's the question. Question 7. I will give you full 5 minutes on this. This is quite a nasty proof. I'm just going to write a couple of little hints on this question now you've had a chance to start it. And hopefully you started with 2n plus 1, 2n plus 3, and 2n plus 5. Now when we do the product, okay, you need to show that you have got the sum of 2 multiples of 3. So try and create 2 multiples of 3 in your sum. And then also try and show it's the product of 3 odd numbers, which is really quite simple. That's for the sum. And then think about what you can do with multiples of 3 in adding these 3 terms together. And you will see you have 2 lots of odd multiples of 3, and think about what happens there. One minute to go. Right, this is really quite tricky. I'm going to go through this one early because my class haven't got anywhere close to working this one out. So we got the product here. So we can see the product is 3 consecutive odd numbers. Okay, we've got 3 consecutive odd numbers. Okay, so therefore this must be odd. So must be odd as 3 consecutive odd numbers. Sorry about that. 3 consecutive odd numbers. Now we can also write it like this. Now I'm just going to, this is 3 consecutive numbers here, because I've taken 3 off that to get the plus 2. Now if I've taken 3 off that, I need to add on 3 times the other 2 numbers. And then what I've got here, this is a multiple of 3. Yeah, sorry, just put it in the right order. So it's a multiple of 3. And this is quite clearly a multiple of 3. Yeah, so if this is a multiple of 3 and this is a multiple of 3, and we've got an odd, that they must be odd when you times them together, this must be an odd. Therefore, we have an odd multiple of 3. Now we can have odd and even multiples of 3. You know, odd multiple of 3 would be 3, 9, and so on. Yeah, and an even multiple of 3 would be 6, 12, and so on. So just bear that in mind as we carry on through the question. So if we sum this, we get 2n plus 1 plus 2n plus 3 plus 2n plus 5. And we can see that's equal to 6n plus 6 plus 3. So that's equal to, we can write this in 2 ways. We can write this obviously as 3n plus 1. And we can also write it as 2n plus 3 plus 3. So this demonstrates that it must be odd. And this demonstrates this must be a multiple of 3. So therefore, it's an odd multiple of 3. So the difference between 2 odd multiples of 3 is going to be an even multiple of 3. Is an even multiple of 3. So let's just think about that. So if you've got an even multiple of 3, you've got 6, 12, 18. You can see quite clearly that all even multiples of 3 are multiples of 6. Now, some students of mine, I think, want to say, what would happen if you did 6n plus 1, 6n plus 3, and 6n plus 5, because these are quite clearly consecutive odd numbers. The only problem is in the 6n bit. So if n is 1, you've got 7, and you've got what we've got 7, and then we've got 1, so we've got 9, and we've got 11. And then you go to n is 2, you get 12 plus 1, 13, 15, 17. And you don't show anything for, say, 9, 11, and 13, and 11, 13, and 15. You don't have all the possible consecutive odd numbers considered by that, because this is quite easy to show what we were trying to show before if we used this arrangement. But unfortunately, it doesn't work because it doesn't show all consecutive odd numbers, just a subset of consecutive odd numbers. So therefore, it doesn't work as a proof. Anyway, that's the end of that sheet. Look forward to seeing you do the next sheet, which will be on Monday at 4:45. Anybody does further maths, I'm going to have a go at my first further maths revision session tomorrow at 4:45.